Okay. I don't really know what next generation means, but this was just born, so I think it is the coming generation in that sense. Um, I work for a company called Foyer Labs, and so what we do is we offer a service for managing connected devices. And the idea there is to bet on the revolution that we're about to see, where, to quote, for example, the CEO of Ericsson, we expect to see like 50 billion connected devices by 2020. That just about anything that can benefit from being connected will be connected. Now, obviously, this is going to create a need for solutions to manage these devices in terms of configuration, monitoring, software upgrades, things like that. And so our idea is to try to come up with a solution that is hacker-friendly, so that you can, as an entrepreneur, at least that would be the audience here, right? People who get a device, they want to get going, get a prototype up with their cool idea in a day or two, and hopefully then, within a very short time, be able to demonstrate end-to-end functionality with business logic in the cloud, software on your prototype device, and go to investors and get lots of money. So, so we have a software stack on the embedded side that we call ExoSense device, and then on the server side, ExoSense server, and customers can buy their own standalone servers and run them, or eventually we're going to field a hosted solution, device management as a service. So, and one of the challenges is to be able to get good rate plans for mobile communication, things like that. So we're also cooperating with solutions that can provide global roaming data plans that are economical, things like that. So our domain, automotive is one example of where we have some initial customers and so far prototyping projects. And telematics is sort of the word for collecting data points from the vehicles, where you would have a device, a telematics device inside the car, connecting to the CAN bus, collecting whatever data on, for example, battery performance or GPS waypoints, things like that. And then the telematics server. Now we have a need for a database in both ends. I'm looking at the coming slide on this, where on the server, obviously we're aiming to handle millions of connected devices. So there we need high volume, high performance, scalability, redundancy, bunch of stuff. But we will have fast disks and lots of storage space. Of course, on the device side, we have small footprint, usually a very slow disk. We want to conserve energy, and there is no redundancy. There is very little concurrency. So it would seem like a stupid idea, right, to use the same database on both sides. But there are actually some points to it for us. One thing is that some of the features that I'm going to show you, we're actually using them both on the device side and on the server side. So we are actually running exactly the same code. And that's quite useful. So, just to summarize, I will go through some of the features of this and also tell you what works and what doesn't. And then I'll give you a GitHub repos, and then you can decide whether you want to use it or not. So KVDB was originally the working name, just key value database, very imaginative name. It started out as a thin layer on top of LevelDB, and we were thinking that we would, say, run LevelDB on the server side, maybe SQLite 3 on the device side. And we wanted to have a common API for multiple backends. And we decided that we're just going to deal with ordered set semantics. So you can write new backends, but it has to be ordered set. And right now, the backends we support are LevelDB through eLevelDB, which is maintained by Basho, and SQLite 3 and ETS. And we support transactions so that we can have atomic commit and rollback. And we also have a special API which supports sort of a structured key abstraction. Because when we deal with configuration data, excuse my husky voice, by the way, I caught a cold a couple of days ago, and probably made it worse with a few glasses of whiskey last night. But anyway, the structured key API allows us to deal with hierarchical data in a convenient way. And just about all configuration data is tree structured. Persistent queues, because the devices we manage go offline and online. Essentially one of the key services we support is that if you, from your business logic, want to talk to your device, you can send an RPC and we will queue it, and then when the device comes online, we will dispatch the RPCs and then deliver the results back. And that also leads into needing some timing services. You may, for example, want to push an RPC, but you want it to time out after 10 minutes or 24 hours or whatever. Or maybe you want to have some scheduled retries or whatever. So we implemented some cron-like scheduling features as well. Indexing is always nice to have. So we support that. I'll show you a little bit about how the indexes work. And then just a few words about the pluggable schema support. So there are a lot of advantages to just hardwiring an ordered set assumption. And luckily with stuff like LevelDB, we can now do high performance ordered set. Well, actually we could do that 15 years ago with ISAM files. And but anyway. So all the backend plugins have to support ordered set. And when you create a table, you can specify how you want to encode the objects, and especially the keys. And we have two ways of encoding it. Either you use Sext, which is a library I wrote that allows you to serialize Erlang terms in a way that preserves a sort order. So that means with Sext encoding, you can use any Erlang term as a key, and you will get the Erlang term sort order on disk. With raw, well, it's just, then the key has to be a binary, and then you get whatever your typical string sort order. So all the objects are either key value pairs or key attributes value pairs, and the attributes list is just a list of key value pairs. So we have a table abstraction, So if you use LevelDB, that is your entire database, and within that you can create virtual tables. And you give with options. Actually, we use the encoding option to determine whether it's a pair or a triplet. That may not be so elegant, but it works. And so then you can have, for example, sext encoding of the keys, and you can have raw encoding of the value part, or Erlang term encoding if you want to. So if you have raw encoding, obviously you can only write binaries to that field. So LevelDB is fast. We haven't used it on the devices yet, but I know some people actually do. One worry we have is that it creates a lot of files, but that may not be a problem. Our plan to use SQLite, well, we ditched that pretty much because it's so slow, especially since we're actually generating SQL queries. I guess there are low-level APIs, but it was a lot easier to use the SQL interface to get it working. But it's dog slow, so we don't want to use that. So what we did was we created an ETS backend with transaction logging. So you actually get persistency if you turn on the transaction logging. And that seems to work reasonably well. Now, transactions, they work fairly similarly to Mnesia transactions, where you have the API functions. I don't have anything to point on. The database operations will sense whether they run in a transaction context or not. But not like with Mnesia, that if you use Mnesia read and it's not within a transaction, it's just going to exit. If you're not within a transaction, it just writes directly to the database. We have two different functions for transactions. One is in transaction, that's the one we use most of the time. It basically says, I need a transaction context for this. If there isn't already one, I'm going to create one. But it will reuse an existing transaction context. If you call kvdb::transaction, it will start a new transaction context. So then it will be a nested transaction if you're already in one. Otherwise, you get a fun, or you provide a fun, kind of like with Mnesia, but it takes an argument. And this is actually your database instance. You could say it's the DB variable is a record that defines the database. And in this case, it's a database where you have an ETS backend on top of your original backend. So it's kind of a pair of backends. So the ETS backend doubles as a transaction store, which was actually nice when we were implementing it. So one thing that I think is a bit original, and you don't want to do this in Mnesia, for example, is that you can actually pass this transaction context to another process, and it can operate on your transaction store. So we're using that to, for example, if we create a user in our system and we want to populate certain devices, we have some security checks in there so that you cannot perform certain operations unless you are actually signed into the session manager, which is a separate process. So then what we do is we call on the session manager to authenticate the user. But of course, the user hasn't been committed to the database yet. So then we pass the transaction store, and it reads the transaction store and and creates a user session. And that feels fairly Erlang-y. Now, obviously, or at least right now, because we're not actually using locking yet. I'm working on the lock manager, and I'll get back to that. So you have to be a little bit careful with your concurrency. But normally in this case, for example, we just do a gen server call, and then we wait for it to do its thing, and then we get control back, essentially. And then we can continue with the transaction. The KVDB conf API uses structured keys, where we use an asterisk as a delimiter. And we have functions too, kind of like with a file name API. You can split and join parts and create or inspect keys. And it also uses escaping. So if you would say you would have a device name or whatever that happens to have asterisks or any other funky characters that we don't consider, then we will actually escape them in a way that doesn't break the sort order. Now this also allows us to use first and next in the database so that you can actually skip over an entire subtree. So you can traverse a data structure at sort of the same level in a tree. Because with the escaping, we will know, for example, that we can use just attach a character that we know is greater than any valid unescaped or escaped key character. So then we can just jump over a lot of data. We also have functions for reading an entire subtree and then sort of replanting it under a different root or in a different table. I have an example there. It's a bit small text, but up there we're starting KVDB. I open an ETS backend. That's nice, especially when you do demos. Now it's RAM only because I'm not logging to disk or anything. I write a few key value pairs here, or keys where one is A star 1 star X and bracket. That actually is a netconf style list or array. So you can have, if you have leaves that are basically anonymous, then this is a way to store them in the tree. So then obviously I can read back an object, and here you can see that it actually sort of normalizes that index a little bit. But I can also read an entire tree. If I say read everything under A, it will give me a configuration tree record with the root and then everything under the root as a tree structure. And if I can, for example, shift the root up and down in the tree if I want to, or I can just say right tree and provide another root, and then I will get the same subtree, but someplace else in the. So we use this, for example, when we want to push configuration data to a set of devices. So then we take the configuration data and we put it in a cache table. So we just read the tree and just put it in a cache table together with reference counting for each device. And then as we can contact the devices, we will just take that cache object. And then we use the same database on the device, so we get this structure and we just put it in the table on the device side. Now the queues. So when you create a table, you can give it type FIFO or LIFO if you want to. What happens when you push an object to a queue is that it creates a special key using a microsecond timestamp. So you get the objects in insertion order. And then you can pop, you can peek into the queue, you can list objects in the queue. You can also hide objects in the queue if you want to, that they remain in the same place, but you just toggle a flag so they become invisible, and you just skip over those if you want to push or pop objects. You can also create a queue that's keyed FIFO, for example. Then it will take the object key and put in front of the timestamp. So then if you pop, it essentially becomes a priority queue. So it will take them in key order and insertion order. And of course, this also means that we can store timers. There is a server that sets Erlang timers, basically uses this persistent queue to sort of pop the next timeout, or look at the next timeout in order, and then set an Erlang timer. If it's too far away, it will set a timer to just look again and set a new timer until it's close enough to actually reach the time within one Erlang timeout. So we have a library called KVDB Cron, where you can add a timer, and then we have a little grammar where you can specify how long you're going to wait, and also if you're going to have a repeat timer, how many times you're going to repeat until a certain deadline. And then just what function to apply. Here I'm applying a test function, which is sort of handy for testing that the timers work. So in this case, it fires 3 times with 3-second intervals. That's what that means. And just to illustrate the timer expressions, you give a time spec and then a repeat expression and until expression. Or you can just simplify it. So if you don't have a final time, you don't have to add that. Or if you want to be really lazy, you can just add a number and that will be in milliseconds. So, for example, you can write in 2 hours, 3 minutes, and 2 seconds, and then repeat until 1845. And you have like daily, weekly, monthly, last day of month. I don't know if anyone can think of other useful schedule expressions. We can certainly extend the grammar. So the indexing, essentially you index on the attributes or on the whole object. So you give an option where and a list of the attributes that you want to index. And if you just provide the name of the attribute, then the value of the attribute becomes the index value. If the value of the attribute is a list, then you can use, for example, each. So you say the name of my index is skill, and each element in the list of the skills attribute is going to become an index value. Or if it's a string, then you can just create a word index. So as an example, say I create an object where, a person object with some skills and tags. I can do an index get and find the object. So the one variant I didn't show here was that you can provide a callback function that can either get the value of an attribute or the entire object, and then calculate a list of index values. So it's semi-tricky to index a tree structure where every leaf in the tree is a separate object in the database. So then we use a callback function that, for example, inspects the key to see, is this a name leaf or whatever type of leaf that I want to index, and then it can emit an index value. Otherwise, it just emits the empty list, and the leaf is unindexed. So that seems to work fairly well. So you provide a schema callback, and right now the schema behavior has 4 callback functions. One is validate, and that is called first on, for example, if you want to update an object, first schema validate is called, and it's supposed to return a new object. So there you can modify the object or do type checks, whatever. Or insert automatic attributes if you want to have vector clocks, things like that. On update is after it's written, where you can have, in this case, what we do is when you've pushed something to a queue, we omit an event to trigger the dispatcher if it goes from empty to non-empty. And also we have pre and post commit. So, still a lot to do, but we figured it's time to publish it because we feel it's pretty useful. The big thing, I think, is to integrate locking. And until I have locking integrated, I don't think it's a great idea to run this. Well, actually, you can't run it distributed because it doesn't have replication and things like that. And you may want to think about the use case. If you have a lot of concurrency, a lot of people hitting the same data, you may want to wait for the locking to be implemented. Or you can just write a schema plugin that uses some other locking. I'm going to make the locking a separate library that is useful in its own right. And also for the distribution and recovery, I'm going to implement log merging. We probably will implement support for geographical redundancy, things like that. But we're doing it in priority order for us. So for now, we can actually get by without the locking. And one little safety feature is that commits are serialized. The database instance process is sort of a synchronization point for commits. So you commit one transaction at a time to the back end. And this is also a synchronization point for log switches. If you have the logging turned on the ETS table, you can set a log switch threshold where it will start on a new log file, and it will also take a snapshot, for example, of the table. Reasonably similar to how Mnesia disk copies work. And I think we will support a couple of different distribution patterns. Now, so we're going for consistent or transaction consistency here. And one problem there is to come up with a good distributed locking algorithm that doesn't limit scalability completely. Now, Amnesia, for example, solves the deadlock detection problem by using deadlock prevention, which scales reasonably well because it doesn't have a central dependency graph. But you get phantom deadlocks and transaction restarts. And since you have transaction restarts, you cannot do what I did in a previous slide where I passed the transaction context to another process and things like that. You cannot do side effects inside a transaction. I want to do side effects inside a transaction. We do lots of side effects. So I want to have an algorithm that does scalable deadlock detection and basically aborts on deadlock, because there should never be a deadlock in a well-designed system, I think. So I have an algorithm for that. I actually wrote it back in '93 when I first started using Erlang and I needed a distributed database. I didn't actually finish it, but I did design a locking algorithm and then chided myself because if I had just bought a good book, maybe I could have avoided 3 days of headache trying to think it through. But then I dusted that off a few years later, and Thomas Arts and I, Thomas, who is a partner in Cubic and quick check expert and also expert on formal verification, he actually did model checking on this algorithm and tuned it a little bit and showed that it was both sound and minimal, actually, so it scales well. So I'm in the middle of rewriting it because I needed to make the lock manager a little bit more powerful. For example, since we have tree-structured data, I want to have tree-structured locking so that you can go in the middle of a tree and lock a subtree, for example. So it's essentially instead of just being table and object locking, it's a generalized hierarchical locker with read and write locks. So the idea, this is a cooperative locking algorithm that depends on the locking agents, the transactions, being essentially actors who can talk to each other. I wouldn't want to implement this in any other language than Erlang, basically, but it works well in Erlang. So the idea is, there was apparently animation here. I thought that I had turned that off. The idea is that the lockers will not just say if you had a lock or not, it will actually return the queue of all transactions that are waiting in line for that lock. Usually that's probably a list of 1. But if, for example, in this case, transaction 1 holds lock A and transaction 4 is waiting for it, and transaction 3 is holding lock C and waiting for E, for example. So, and this is a deadlock situation, but none of the actors have enough information to actually detect it. So what they do is that since, for example, this transaction knows it has a direct dependency, or 4 has a direct dependency to 1, and of course we know that 4 knows that because it's also gotten the wait list, and I have a dependency to 3, so what I do is I inform transaction 4 of this lock that it's not involved in. So it's kind of like a fill-in-the-blanks algorithm. And if you do this in the right order, you will, with a minimal amount of messages eventually get to the point where one transaction has enough information to detect a deadlock. And in that case, you can either just surrender a lock to another transaction so that it can complete, but in the case of KVDB, I think the right thing to do is to simply abort. So it will support both modes. I'm also going to try to use this, for example, in gproc, because it occurred to me that you can do leader election this way. If all instances just grab the same lock, usually one will win. I mean, there will be a deadlock, but it will be resolved. So one will come up with a lock every time. And you can also then detect partition networks that way, so you know that you can resync. It's coming. It's not coming today or tomorrow, but eventually. Let me... That's what you get when you copy-paste. They think you actually want all the animations as well. There we go. So that locker library is going to be called DDD. It hasn't been published yet, but it's for distributed deadlock detection. And the idea is you should be able to use it also. Say you're using React or something, you should be able to use this, I hope, in a fairly scalable manner, since it's a protocol-based, fairly well-contained locking algorithm. And I'm building in quorum support and things like that, so that you can, for example, require locks on a majority of replicas, things like that. But work in progress. So this is where you'll find it, Fourier Labs with a capital F. Doesn't matter to HTTP, but it does matter to Git. KVDB, and it's an MPL 2.0 license. And that's the license we're going to use for our open source stuff. And we chose that partly because we do want people to contribute back. So this is similar to the Erlang public license, but it is, it's an OSI approved license, so it shouldn't be a problem in that sense. It is also prepared to be GPL compatible, which we also think is a good thing. So it should play well with your proprietary software. It should be able to play well with GPL software. And so we think it's a pretty good license. Any questions? Yes?
Are you going to replace GenReader with DDD?
I'm going to try. Well, in gproc, yes.
Right.
That's my... I'm going to try to do that. And if it works out well, then yes.
So
But
does DDD use distributed Erlang to negotiate? Like,
yes.
So, and you can say, I want, if I know, so each node has a lock or something, if you want to do leader election, then if you kill the majority of the locks, you become the leader, or you require all the locks and then...
I'll sit down and meditate over exactly how to do that. I think I thought I figured it out a few months ago, and then I kind of dropped it, and I've had other things to. So I don't remember exactly what it was that I figured out. But I think it will come back to me. So yes, it uses distributed Erlang. I've thought about making that optional, but I don't know. For a while, I thought that if I specify it as a protocol that's not Erlang centric, you could possibly use this also in cross-language environments. But let's say that's not a priority. it's enough of a headache to get all the pieces working together. So yeah, it's going to use distributed Erlang for now. Any more questions?
We have plenty of time. Don't be shy.
Do you have any performance numbers?
Do you want-
incorporate SQLite?
Performance numbers. Yeah, SQLite, it just sucks. I've done some performance measurements. Let's say I haven't spent a lot of time trying to optimize it, and especially not, say, for simple transactions on a RAM-only database. I did a test where I was doing the same thing in Nisia, and the transaction startup time in KVDB is significantly longer than in Nisia. So for simple stuff where Nisia fits well, it is definitely faster. I have prioritized functionality. I don't know how far I can optimize those things. But we've focused on some other things. For example, the queuing system. The idea there is essentially we have one output queue for every device, and we plan to support millions of devices. So creating a new queue and pushing an object into it is dirt cheap. So some things are very scalable and very cheap. Other things, maybe not so much. So, for example, there are some fairly cool things. You can create tables inside a transaction and populate the tables and then commit it all. But that also means that it needs to check, sort of pull the table metadata into the transaction store and things like that.
Did you use
So-
caching? Did you cache metadata?
Some. So that's an area where I could optimize a bit. But no, the getting top-notch performance has not been our priority so far. So we follow Joe Armstrong's advice and make it as slow as we possibly can. Okay?
How do you represent these trees and how do you update them?
The trees, where were they? Oops, sorry. The trees are represented by, with the structured key. So every leaf in the tree is a separate object. So the tree structure is in the key. And this is one area where you really want the ordered set semantics. Because to read a subtree, you just basically go to the top and then you just next your way through the tree. And
What if you want to update some leaf?
you just write that object. You create a key that represents the leaf and you write it.
But this has to propagate all the way up to the root that.
No. So you can do similar things in ordered set ets, for example. That if you have a structured key, so the root is here's the root and then star and then the next one, and it will actually sort so that all the tree objects will just be laid out. So if you walk, say you go to A star 1 and then do next, you will actually find this element. So you can, and if you want to skip that subtree, what we do, I think we put a semicolon after the star, and that's going to be bigger than any key part that is an actual subtree object. So then you just jump to the next subtree or out of the tree entirely. So this is where ordered set semantics actually works really well.
I'm still missing something, but I don't want to.
Yeah. Did you have a question too?
Yeah, so how do you query secondary indexes, but how do you define them?
Excuse me, how do you?
How do you define secondary indexes? I saw the part where you had to query for index.
How? Yeah, that was this option. You have an index option, and then you list your indexes. Basically, name the attributes, or name sort of the index, and then refer to the attribute and say what you want to do with that attribute. So that's how you do it. Another thing that we're trying to do is, as I started looking into it, is to integrate XPath. Because if you're dealing with netconf XML objects, you can fairly easily store configuration trees this way. And XML or netconf uses XPath to refer to nodes in the tree. So XPath is a query language for XML documents. So I'm going to try to add XPath support as a way to query these subtrees. Any other?
Got about a minute remaining.
Yes?
So what would you say are the key distinguishing characteristics versus Amnesia?
So for one thing, you can use side effects inside transactions without losing your sanity. That is, now with Mnesia, there is actually a patch that Erlang Solutions and I and Klarna did to Mnesia, where we added backend plugins. So for example, LevelDB was one backend supported. And there I also added similar indexing capabilities. So you could have indexing callbacks and things like that. So with that, actually the difference is smaller, but I didn't see that patch in R16b, so I guess if you're interested in it, buy Don Gudmundsson a beer or two and try to get him to actually release it. Klarna has been testing it, and it seems to work pretty well. But otherwise, you could do a lot of these things in Mnesia as well. The reason why we didn't pick Mnesia is that if things go well for us and we grow to really huge scale, we pretty much know that Mnesia is not going to stay with us. We know what pains we're going to have to suffer. So at least now we're inventing our own headaches, which is a consolation. But we did discuss using Mnesia quite a lot. And on the device side, I don't know, Mnesia is actually pretty cool. But for us, it was a matter of being able to reuse code and eating our own dog food as well.
Oh, sorry, we're out of time. So if we could thank Ulf for...
Thank you.